Let's make some more force diagrams. This one with the water skier as the first problem. This is the one that, as far as we are concerned in Google Classroom, this is number 2. I know it says 1B at the top here, but never mind that. This is number 2. Draw a force diagram of the water skier. There's a couple ways that you could approach this. Now, first of all, we're going to assume, I should have added this in here, that this water skier is going at a constant velocity, which means, what does that mean? What does it mean in terms of forces? It means the forces are balanced. So if you didn't think about that the forces should be balanced, then I think you should pause the video here, revisit whatever your diagram, what you started with, and give it a try. And there's two ways I think that you could approach this. You could say, like, here's this tension force of tension on the skier from the rope. And of course there's force of gravity on the skier from the entire Earth. And then, like, what about what's holding them up? You know, what about this and this? Well, these are coming from like a combination of the force and the skis, right? You really don't need to think about, like, the person is not actually touching the water. The person is on the skis, and the skis are on the water, and we're making a diagram for the water skier. So that means that for the water skier, there is a support force. And look at the angle of the skis. Support forces are always perpendicular to the surface. So we'll be going up like this. So that's a normal force. Sometimes I say support force, normal force. Those are the same thing, interchangeable. And if you called it a support force, I would not ding you for that. So that is the normal force on the skier from the skis. Skis? I put 2 I's there. Oh, whatever. Not spelling class. Skis? That looks weird. Whatever. Okay, now the thing that we want to try to practice a little bit for the first time here, if you look back at the reading that you did, this here, what direction is this person moving? Is this object moving? In this case it's a person. They're moving this way. So that direction of motion, or direction of possible motion, in this case they are moving, that's going to be the direction of one of our axes. So I've got a horizontal axis. The axes always go through the object. That's always going to be your origin, where you make your dot there. And then, of course, the other axis is perpendicular to that. And once you have those dotted lines figured out, anything that is not along the dotted lines, you are going to break up into its x and its y components. And those must be dotted lines, not solid lines, because they're not like extra forces. It's like the 2 parts of that force. So just like you were plotting a point, right? You're going to go over this much and up that much. And now we can see how these 3 forces can be balanced, because now this here, that must be the same as this, right? So the horizontal is balanced, and then this must be the same as this. And eventually when we start to do this with numbers, that's going to be real important. And then you're like, well, what about this? Well, we broke this up into those 2 things. So this is an either-or situation. You can either think of this as this normal force pointed up here, or you can think of it as its 2 parts, like that. So we're dealing with the parts. Why? Because it's easier to see, like, okay, back and forth is balanced and up and down is balanced. All right, so let's see about this one. So this one looks like we have a tension force here. What direction is this sled moving? It's moving this way. It's not moving this way, it's moving this way. So that horizontal direction, that is one of the axes. And then that's the other one. Of course, gravity doesn't give a flying banana about what's happening. It's always straight down. So there's the force of gravity on the sled. from the entire Earth. All right, and then there's a tension force here. It's a force of tension on the sled from the rope. All right, what else is there? I'm going to assume again that the sled is being pulled at a constant velocity, which means that these forces are balanced. So that should help us kind of think about what's happening here. You could imagine if you were pulling these kids, you probably find a comfortable speed and just pull them along at a constant velocity. So if it's going to be, if there's some pull in this direction, we can go ahead and break this up right now if you want. There's like my X, my Y, breaking it up just like I was plotting a point, right, on this little axis system, over and up. Just like I did here. Okay, so this helps us see now that, okay, the back and forth forces here, this force of, what is this a force of? What would the backwards force on this? Well, it's snow, but there's still going to be friction, right? Force of friction on the sled from the snow. And could this be it? Could this be equal to this? Well, no, because there's also going to be a support force here. I mean, clearly the ground force, it's a normal force, we're going to call that, on the sled. I'm going to say from the snow also instead of the ground to be consistent with that, but it doesn't matter really. Now, what's equal to what here? Well, the left and right has to be balanced, and the up and down have to be balanced. But notice here that there are 2 ups and 1 down. So I think we saw one other example, maybe the last example on force diagrams 1 with that magnet and the nail. So these two, if we were doing numbers, which we're not yet, we're just trying to make nice pictures here, then this plus this would have to equal this. Ups have to equal downs. Right? If you're thinking, oh my goodness, this is so hard, you get better at these with practice, just like anything. Okay, we want to make a force diagram for the table. Right? So here's the table. If this table was going to move, it's not moving, but if it was going to move, what direction would it move? Would it move like down like this? No, it can't move like into the floor. If this person was leaning on it and the table started to slip, it would go this way. So that means my axes, if you're thinking to yourself, well, aren't the axes always just like this? The answer is no, because in a situation like this, if this squirrel started to move, it's sitting still, but if it did start to slip, it would go this way. Or I guess if it started to like scurry up the roof, it would go this way. It's not going to go that way or that way. I guess it could jump, but we're not really interested in that. So in this case, because the possible motion is that way, that means that has to be one of my axes. And then the other one has to be perpendicular to that, so we'll deal with that when we get to a squirrel problem in a minute. But that's just to answer the question, do they always look like this? No. All right. Excuse me. Don't worry, I'm perfectly healthy. The dancer is leaning on the table, making an angle while stretching. So what are the things pushing on this table? Well, of course, there's gravity doing its usual straight down, I don't care kind of thing. Force of gravity on the table from the entire Earth. There is going to be a support force. I don't know, now the person's pushing down here on the table, so let's do this first. That push force is going to be in the direction of their arm. So since all our forces, I can't make it here pointing at the dot, everything has to come from the dot. So that's going to look like this. So that's a force of, what do you want to call it? Push? Sure. On the table. From the person. Or the dancer, I guess. Now that is not in line with my axes. So this is one where I get to make these dotted lines with arrow, dotted lines with arrow. The arrows are important so you can see like ups and downs and lefts and rights and understand what's got to be balanced with what. Okay, so what else we got here? So here I've got these downs. That must be balanced by something up that would have to be equal to those. So I'm going to kind of stretch up through there to try to make it look long enough to balance both this and this. So if we had numbers on this, like let's say this was 2 and this was 4, then this would have to be 6 to balance them. So that's that support or normal force on the table from the floor. If you said ground, whatever, I'm not going to fuss about that. And okay, so we get the ups and downs balanced, and then what about left and right? There must be something here to balance that. What's that? Well, it's friction, right? If there was no friction at all, if this was like on an icy pond, then if you leaned on this, that would just go sliding, and you'd probably slide the other way too. So this is a force of friction on the table, also from the floor. Now, how come I got to make tick marks here, but there's no tick marks on the up-down stuff? Well, the up-down stuff, there aren't two forces that are equal to each other. This plus this would equal this, so there's not really any like trick from geometry for representing that, so we just leave it. We'll be doing this with numbers soon enough. All right. How about forces on this person? If this person were to move, they would go straight down. So that means my axes are straight down, and then perpendicular to that is straight across. Gravity doesn't care. Force of gravity on the person and the entire earth. And then tension forces can only be in the direction of the rope. So this tension force is going to be this, and then this one is going to be the same. See how same I can draw that. Yeah. Did my best. Okay, and now these are pointing like into quadrants. They're not in line with our axes, so those are the ones that I'm going to break up. Always going to do my X first, and then my Y, my X, and then my Y. I think I didn't really make that long enough. Let me fix that. So it looks the same as this one. I'm not going to get out my ruler here when you do this like on a test and make sure that your things are exactly the same. We just do our best with these. Okay, so what's equal to what? Oh, what are these forces? This is a force of tension on the person from the rope, and this is a force of tension on the person from the rope. Okay, so what's equal to what? Well, lefts and rights have to balance, so there's this and this, left and right. And then the up-down, I've got a similar kind of situation to the last one where I've got two up, so this plus this would have to equal that. So there's nothing I can do with the tick marks here. Again, just to help you understand, the reason why we do this axis thing and we break things up into left and right is because then everything is either up, down, or left and right. And ups must balance with downs, and lefts must balance with rights. If you have things at angles, it's hard to see like exactly how things are balanced. That's why we do this. All right, here's that squirrel we've been looking forward to. So this is my recommendation. When you end up with a dotted line like this, which you're going to have anytime something is like on a slope, on a slope, on a slope, things like that, you're going to end up with these slanted axes. This is the order I think you should do things in. Draw the first one that's like in the same direction as the ramp hill, whatever the slant is. So draw that first, and then draw gravity straight down. Do you think that gravity changes its direction when something's on a hill? No, because gravity doesn't care about you or me or this squirrel or anything else. It's always straight down on every object. Force of gravity on the squirrel from the entire Earth. So do that, and then gravity straight down, and now you are going to tilt your paper like this so that this is horizontal. And if you're like, oh yeah, I'm just going to turn my head, whatever, come on, don't be lazy now. It's so much easier to do a good job on these things if you actually turn your paper. Okay? It's easier to make that come straight down when the paper is turned. And notice, if you're looking at this now going like, whoa, that's weird because gravity looks like it's kind of dangling off to the side here. No, it's not. We just turned the paper. Gravity is still straight down, right? But the other forces that we draw are all going to be in line with our dotted lines here. So what else we got here? Well, there is a support force on the squirrel, and the support force is not straight up. It's not this way. It's perpendicular to the roof. So it's straight up this. That is our normal force on the squirrel from the roof. Now, if this roof was covered in ice, the squirrel would go sliding down. It's not, and the squirrel's not moving, so there must be some friction here, and that friction is going to be up this way. Force of friction, squirrel, and that's from the roof. Okay? So how do we see what's balanced with what? Well, gravity, when you have this ramp kind of situation in the slanty axes, gravity is the thing that's actually pointing out into a quadrant. So gravity is the thing where we're going to do x and y, make our dotted lines. And then we can see, oh, okay, this must be balancing with this, and then this must be balancing with this. If you're looking at this and going like, okay, well, that's fine, Mr. McGrath, but like when I made mine, like how did you know that you should make the friction this big and it would be like, you know, it would look about right? Well, I've been making these force diagrams for hundreds of years, so I have lots of practice. If you end up making something and it doesn't look just right, like things are actually balanced, it doesn't matter. I'm not going to fuss at you much about that. If you can make those little tick marks, even if they're not quite equal to each other, even if they don't look like they're equal, you're telling the world, hey, these are equal. All right. I should be reminding you as we go through these that you should be pausing and like doing them yourself. And if you get like to a certain point, you're like, oh, I think I see what you do now. You got to pause me, then you take over, then you try the next one. So if you didn't get this one, and you're feeling like kind of okay about this now, then you need to pause the video and try redoing number 6. Okay? Now, before, well, maybe before you try it, or maybe you've already tried it, draw a force diagram for the skier who slides with negligible friction. So that means we're going to ignore. That means the forces are not going to be balanced. That means this person's going to be speeding up going down the hill. That's what that's telling us. So it's going to look just like our squirrel here, except that there is not going to be any friction. We're just going to leave that out. Okay, so let's try to do the same steps. First thing, make your dotted line that goes in the same direction as the slope. And so I'm really trying to make it like the same direction. I'm not just like throwing down some 45-degree kind of line there. I am really trying to make it parallel or the same direction. Okay, next thing, there's our person. Drop straight down that force of gravity. And you want to put the label, there's like a small angle and like a big angle when you have this kind of diagram. You're going to be better off if you put your force of gravity on the big side where there's more room, because this is going to get crowded up with the that stuff, right? So I get force of gravity on the skier from the entire Earth. Now, I rotate, and I put in, does that look nice in? There we go. There's my other axis. There's no arrows. Don't put arrows on these axes because the arrows we're going to save for forces and the parts of, or components of forces. Okay, so what else we got? I have the support force, or normal force, on the skier from the hill or the snow or the ground, whatever you want to call that. How about hill? And then there's no friction, they told me here. So I'm just going to break up this, just like I'm plotting a point, x and then y. And then I can see, well, there's no motion. The skier is not moving like this way, right? So the up and down, those would have to be balanced. But this right here is this part of gravity, like the down the hill part of gravity, that's going to cause the skier to speed up, like extra tapping on the bowling ball. All right. That's what that one looks like. And how about this kiddo here being pulled back? Now, there's a little bit of interpretation here, and I think that this picture could be maybe a little bit better. What I would like you to assume is that the person here is pulling the kid straight back. So, again, this is a little bit tricky with the, well, if you assume that they're pulling them back in like this direction, I guess there's two ways that you could do this that I would be okay with. Let me do this way. So if, according to what I'm telling you about how to decide where the axes are, when this kid starts moving, they're initially going to be moving this way. Now their direction will change. They're going to be swinging in a circle like that, right? Or part of a circle with a radius of whatever that is. But right off the bat when they let go, they're going to be moving in that direction. So according to what I told you, that means you should do this. And then drop down the gravity. Oops, that's the wrong side. Put the label in the bigger spot over here, force of gravity on the kid from the entire Earth. And then make your dotted line. What are the other forces? Well, there's mom or dad or Aunt Susie or whoever that is holding. Now this is before they let him go, right? So I'm kind of thinking ahead here. If you want to know the secrets of the physics teacher, I'm kind of looking at this, and I guess you could just do those dotted lines now, that your x and your y. I'm looking ahead, whether I've done these already. I'm picturing this and trying to draw this like the same so that I can balance those. So this would be force of P, pull, or parent, or whatever you want to call that, on the kid from the, let's say it's a pull, from the adult person. I suppose it could be a teenager, whatever. So, and then there's also this. That is the force of tension. Or actually, are we doing it for the kid or the swing? For the child on the swing. So if it's a child, the child's not really attached to the chains. The child's sitting on that little bench. So really, this is like a support force. I'm not going to fuss at you if you made that tension. Normal force on the kid from the seat. And that's all balanced. So I was talking about a different way to do that. I think you could also I would not object too much if you did it. I'm just going to do this super fast here. If you did gravity down and you had the person pulling straight back like this, and then the tension here, and you balanced it like this. Like that could happen depending on how this person's pulling back. So that'll be another option. If you're thinking to yourself, well, one of them has to be right, which one is actually right would really depend on exactly what this person is doing. So like you have to make some kind of a guess or assumption about the direction of their pullback. So if you think they're pulling straight back, then it's going to balance out like this. If you think they're pulling up like this, a little bit up to the right, then it's going to balance out like this. All right? Okay, here's a good one. If you're just getting the hang of these slanty type things, then go ahead and pause and try this one again. So there's tried to match that hillside as best as I could. Gravity, don't care. Force of gravity on this climber from the entire Earth. So that's that and that. Now I'm going to turn everything else is going to be in line with this. So there's my vertical axis. You call it a y-axis if that makes you happy. And what else is going on with this person? Well, there's a support force, or a normal force, on the climber from the hill. And there's a tension force. On the climber from this rope. And then if I break this up, then that could be equal to that, and this could be equal to that, and we're all balanced. If you're thinking to yourself, well, hey, wouldn't there be some friction here? It really depends, like the forces in real life, we're simplifying things, not a huge amount, but we are simplifying them a little bit. So it would be possible for this person, because of the rope, to be balanced there only with upward force on them, right? Only this support force. Could they be like using the rope and a little bit of friction from making them slide? Yeah, then this, instead of this being all of the balance with this, there would be like some tension and there'd also be some friction in the same direction. So that's just more complicated. We're going to try to keep things as simple as we can. All right, last two. And I think I'm going to have you skip this number 10. I'll put a note in Google Classroom because that's just a little bit more complicated. I don't want to overcomplicate things for us at this point. Or at any point. Why would you want to overcomplicate things? I think we're doing all right with these. Okay, so if this book were to move, where would it go? Well, that's kind of a tricky question. I guess you'd have to like break this piece off, right? And so it would slide down like that. But it's not going to suddenly like jump off this thing. I guess it could, somebody pushed on it, it could slide up. So it looks like the we got our slanty axes again. And then go ahead and drop your force of gravity on the book from the entire Earth. Drop that straight down. Turn your page. Make your other axis. And if you want to, you can go ahead and break this up into components first. You can do that, and then you can kind of see what the other forces are going to have to be. So there's a support force, like this thing right here is pushing up and stopping the book from sliding this way. So that's a support force or normal force on the book from the, what do we want to call that, a shelf? from the shelf, and then there's another support force from this part of the shelf supporting it this way. So that's another normal force. Remember that normal means perpendicular on the book. Also from the shelf. Different part of the shelf, but it's still the shelf. Right? And that could be equal to that. We're all balanced. And never mind walking. Walking is like super complicated. So there you go. Oh, I went over 30 minutes. That means that you get a free pizza.